Going to be talking about exponential decay. So first thing I want to do is just look at what exponential decay is. It's really the same as exponential growth, except this time we're going to be going down instead of up, and we're going to talk about things decaying or going down. So here is your equation for exponential decay. So you have the same equation as exponential growth, but notice that instead of a plus sign, you have a minus sign. So y is equal to c times 1 minus r raised to the t. C is the initial amount. R is the rate of change. Remember, not as a percent. You want to make sure that you are converting that into a decimal. And lastly, T is going to represent the time. Okay, your C value is also going to be your y-intercept as you're going through and doing these problems. So to start off with, let's take a look at just graphing some exponential decay problems. So when you have your C is 16, okay, so we're going to have y is equal to, well, my c is 16, and then I'm going to do 1 minus my rate, which is 0.45, and that's going to be raised to the x power. Now, for whatever reason, when I do exponential decay, I really like to do, when I do my charts, do -1, 0, 1, 2, 3, and 4. That's just how I've always done it. I like to have the -1 there because a lot of times it actually is on our graph. So that's what we're going to do, exactly like we did with exponential growth, is we're going to plug that into our calculator and we're going to continue to change the exponents. So first you're going to plug in -1. Well, when you do that, you get 29.09. Then you're going to plug it into your calculator again, and you're going to plug in 0. I really suggest you plugging it in your calculator along with me, so you make sure you're doing it correctly. Likewise, make sure you know where all the buttons are on your calculator. If you don't, come ask me. And when you plug in 0, you get 16. When you plug in 1, you get 8.8. Plug in 2, 4.84. Plug in 3, 2.66. Plug in 4, 1.46. So let's go ahead and let's graph this. So -1, 29.09 is going to be off our graph. So let's go ahead and jump to 0, 16. So we're going over 0 and we're going to go up 16, which is right here. Then we're going over 1, up 8.8. So when we go up 8.8, we're going to be almost going all the way to 9. Then when we're going over 2, we're going to go up 4.84. So that's going to be almost all the way to 5, which is right about here. Then we're going to go over 3. We're going to go up 2.66, which is almost all the way to 3. Then we're going to go over up 4, and we're going to go over 4. Oops, this one should be over here. Oopsies, silly me. And then when we go over 4, we're going to go up 1.46, which is almost like going up 1 and then halfway. So now that I have those drawn, I can kind of draw a decay model, which hopefully yours is better than that. That was pretty bad. So then what you're going to do is you're not going to cross the x-axis as you're coming down. You're just going to kind of come down to it, and then you're going to sit on top of it. You're not going to actually cross it. So let's take a look at number 2. So now we're given that our r is 30%, which we know we need to convert to a decimal. So when you move the decimal left 2 places, you get 0.30. So our equation is going to be y is equal to 15 times 1 minus 0.30. That's cool. Why don't you go ahead and do that while you're at it? So we're going to do 1 minus 0.30. Well, that could also be written as y is equal to, so 1 minus 0.30 to the x power. That could also be written as 0.70 to the x power. So now we're going to go ahead and we're going to graph. So I have -1, 0, 1, 2, 3, and 4. So I'm going to go ahead and plug all of those in. Well, when I plug in -1, I get 21.43. When I plug in 0, I get 15. I plug in 1, I get 10.5. When I plug in 2, I get 7.35. When I plug in 4, I get, oops, I got off. 7.35. 3, I get 5.14. That's what I meant to say. Just kidding. And then for 4, I get 3.60. So now we're going to go ahead and plot those. So if we're going over 0 and up 15, we're going to cross that point right about here. Then we're going over 1, up 10.5. So we're going halfway to 11. Okay, then we're going over 2 up 7.35, so that's going to be just a little past 7. Then we're going over 3 up 5.14, so that's really barely past 5. And then we're going over 4 up 3.60, so that's just about just over halfway to 4. So this is going to be coming on down, and it's going to slowly come down. But again, it's not going to cross that x-axis. You want to make sure that you don't do that. So let's take a look at some decay word problems. So we're talking about a raft, and it loses 6.6% of its air every day. Well, again, we want to convert that as a decimal, so we get 0.066. The raft originally contains 4,500 cubic inches of air. So first thing we want to do is write an equation that represents the loss of air. So what we're going to do is we're starting with 4,500, and then it tells us that we're going down. So when it's talking about decreasing, going down, then you know you need to use exponential decay. So 1 minus 0.066. Now that's going to be raised to the x power. So now we can go ahead and we can fill in and subtract that. So y is equal to 4,500 times 0.934, because that's what you get when you subtract those. So now we want to estimate how much air is going to be lost after 7 days. So I'm going to take that equation that I had written, and now my x, my time measurement, is going to be 7. So I'm going to plug in my exponent as 7. So you want to make sure that you are plugging that in correctly. So when you do that, you end up getting 2,790.23. You can have a decimal here because you can have a percentage of a unit of air. That's what I was trying to say. If I could spit my words out today, that'd be fantastic. Okay, so that's your answer for part B. So let's go ahead and let's take a look at number 4. Let's read it together. During the past several years, the population of Campbell County, Kentucky had been decreasing. Okay, I need to use exponential decay at an average rate of 0.3% per year. Well, I still need to convert that to a decimal, so I still need to move it left 2 places. So that's going to be 0.003 when I convert it to a decimal. In 2000, the population was 88,647. Write a decay equation that represents the population since 2000. Then, assuming the trend continues, estimate the population in 2013. So we're starting with 88,647 people. And then we're going to do 1 minus 0.003 to the x power. And that's going to equal the population. So I'm going to go through and actually subtract that. And when I do that, I end up getting 0.997. Now I want to figure out how many years passed between 2013 and 2000, and that's going to be 13 years. So now I'm going to take that in the equation. I'm going to do 88,647 times 0.997, and that's going to be raised to the 13th power. And when you do that, you get 85,251 people. Now remember, when we're talking about people, you always want to round to the nearest person. Please do not tell me that it contains 0.6 of a person. That's not a very nice thing to say. Okay? So let's go ahead and let's take a look at number 5. Did I skip over it? No, I don't have it in here. Okay, so number 5 says, during an economic recession, a charitable organization found that its donations dropped by 1.1%. So we're going to take that 1.1% and we're going to convert it to a decimal. So that's going to be our R. This should be a 1. Okay, so that's our rate. And then it's starting at $390,000. And so if it's dropping, that means we need to use an exponential decay equation. So we're going to do 390,000 times 1 minus 0.011. It asks us to estimate the amount of donations after 5 years. So then we're going to divide it out like so. And when you subtract, you get 9.89 to the 5th power. So now you can go ahead and plug this in your calculator. Now remember, when talking about money, you want to make sure that you use 2 decimal points. So plug it in your calculator, make sure you did it correctly, and it should look just like that. Now, let's go ahead and let's take a look at when you know the following are exponential growth or decay. So before we do that, I kind of want to make a list of words that you can put. So I'm going to put G for growth and D for decay. So if it's going to be a growth problem, somehow it's going to imply that it's going up. If it's going to be a decay problem, it's going to imply that it's going down. Okay, so growth, one of the things you might see is appreciate. Whereas if it's going down, one thing you might see under decay is depreciate. And I do suggest writing these down because you'll see these. These are key words to look for in a problem. Okay, this might say increasing for growth, and this might say decreasing for going down. You could also see going down or going up. So those are just some tips to kind of get you started. One thing you can also look for as well, when determining if an equation is growth or decay, you need to look at whether the number in the parentheses is less than 1. So for example, the number being raised to the exponent in this one is greater than 1. Okay, so that means it's going to be growth. Then, taking a look here, the number being raised to the exponent is less than 1, so it's going to be decay. Here, my actual number that's being raised to the exponent is 0.75, and that's less than 1, so that's decay. Here, 4 is being raised to the exponent, that's larger than 1, that is growth. Here, 5 is being raised to the x power, that is more, and so that is also growth. Okay, so that concludes your note video for today. Thank you for listening.